In the previous video we saw that for an IIR system, h of z could be evaluated for all values of z except when z is equal to 0, and that by evaluating the magnitude of h of z for different values of z, we could build up an image of the surface of the magnitude of h of z. Before dealing with the case of IIR systems, I'd like to highlight an important point which can cause some confusion at first, which relates to an infinite series. Consider the following situation where we start with the square of area 1 and we keep dividing the square into smaller and smaller sections, whereby each section is half the area of the previous section. I hope you can appreciate that we could just keep creating new half sections forever, and each new section would just keep getting smaller and smaller and smaller, so we would have an infinite number of sections which are continuously getting smaller. Now consider what would happen if we started to add up all these half sections. We'd have a half plus a quarter plus an eighth plus a 16th and so on. If we then started summing the areas of all these possible sections, then the answer would get closer and closer to 1 the more and more section areas we added up. In fact, if we were able to add up all the possible section areas, the answer would have to be 1, since the original area is 1. The reason I point this out is because an infinite sum of terms can be determined, even though there are an infinite number of terms. This can be confusing because you might assume that if you had an infinite number of positive, non-zero values and you sum them up, then the result would have to be infinity, and I hope this example shows that this isn't the case. If an infinite sum of terms can be determined, then the infinite series is said to converge. In general, you can tell if a series is converging if the numbers are getting progressively smaller. It's also worth noting that if you were to sum up just 10 of these terms, then the answer is very close to 1, and that the sum of just 10 terms is a close approximation to the actual answer of 1. There are of course situations where an infinite sum expression doesn't converge. Take for example the following case, where we're now summing the sequence 1, 2, 4, 8, 16, 32, 64, 128 and so on. This sum of terms doesn't converge as the numbers are getting progressively larger, and therefore the result of the summation cannot be determined. Okay, now let's get to the situation where we're dealing with IIR systems. In this example, the impulse response is 1, 0.5, 0.25, 0.125, 0.625 and so on, where the current output is half the previous output and it continues on forever. In general, the impulse response of these type of systems can have an infinite number of non-zero terms due to feedback in the system. A consequence of this is that when we consider the Z-transform being applied to this type of infinite impulse response, we need to work out if the Z-transform converges or not. What we'll find is that the Z-transform will converge for some values of Z, but not for others. I'll go through a few examples of how to calculate h of z shortly, but it might be useful to visualize the surface of the magnitude of h of z for this system before doing that. First of all, you notice that the z surface is missing over a certain range of values. Looking from above, this region of missing values is circular in shape. What we're going to see is that for values of z that lie inside this circle, h of z cannot be determined. For values of z that lie outside the circle, h of z can be determined, and this region is known as the region of convergence. I'd also like you to notice that the circumference of the circle of missing values passes through what is referred to as a pole. The magnitude of h of z close to the pole is approaching infinity in the region of convergence. Also make note that the pole is at the location z is equal to 0.5 plus 0j. This is relevant for later on in the video. Now let's take a closer look at some calculations for h of z in this example system for a few different values of z. When we evaluate h of z when z is equal to 0.6 plus 0j, we can see that the product of h of n and the signal z to the power of minus n is decreasing and therefore converging. The plot in the bottom right corner shows the signal h of n multiplied by the signal z to the power of minus n. Since these product terms are converging, h of z can be determined and we can get an approximate value of h of z at z equal to 0.6 plus 0j by summing the first 50 terms of these products, and we'd get a value of 5.9993. If z is made smaller, 0.55 plus 0j in this example, then the product of z to the power of minus n and h of n results in summation terms that decrease at a slower rate, as illustrated in the plot. Also note that the magnitude of h of z has increased when z is equal to 0.55 plus 0j, as we are now closer to the location of the pole, which is located at 0.5 plus 0j. If the value of z is further reduced to 0.5 plus 0j, then the product of z to the power minus n and h of n results in summation terms that all equal 1, and the magnitude of h of z when z is close to 0.5 will be approaching infinity. Again, recall that for this system there is a pole located at the location 0.5 plus 0j. If the value of z is reduced further to 0.4 plus 0j, you'll notice that the product of z to the power minus n and h of n results in summation terms that increase and don't converge. Therefore, h of z cannot be determined when z is equal to 0.4 plus 0j. If we go through the same process for z having complex values of 0 plus 0.6j, 0 plus 0.5j, and 0 plus 0.4j, you'll find that the product of z to the power minus n and h of n will decrease, stay constant, and increase respectively as shown. We'll get three similar results for z having values of 0.4243 minus 0.4243j, 0.3536 minus 0.3536j, and 0.2828 minus 0.2828j. What we're seeing is that for some values of z, h of z cannot be determined. The values of z for which h of z can be determined is known as the region of convergence. If we go back to the plot of the surface of h of z shown earlier, you'll notice when I show the locations of z that we've just explicitly evaluated, that the values of z that correspond to constant summation terms are all the same distance from the origin, and that they all lie on the circumference of a circle that passes through the location of the pole. The pole is located where z is equal to 0.5 plus 0j, and as stated earlier, the magnitude of h of z close to the pole is approaching infinity in the region of convergence. h of z can be determined for all values of z that lie outside this circle, and this region outside the unit circle is known as the region of convergence. For values of z for which the magnitude of z is less than 0.5, you'll find that the product terms of h of n and the signal z to the power minus n progressively increase, and that the magnitude of h of z cannot be determined. If we look at a second example in which the system has more than one pole, we can see that h of z only converges for values of z for which the magnitude of z is less than the magnitude of the largest pole location on the pole 0 plot. In this example, there are three poles located at 0.5 plus 0.6j, 0.5 minus 0.6j, and 0.3, which are a distance of 0.781, 0.781, and 0.3 from the origin. Note that h of z only converges for values of z which are more than 0.781 units from the origin. For values of z which have a magnitude less than 0.781, the system doesn't converge and h of z cannot be determined. If we take a look at a final example in which we have an unstable system, you'll notice that the product of h of n and the signal z to the power minus n will converge for values of z which have a magnitude greater than 1.1. Also note that the yellow unit circle is not shown in the region of convergence. In general, for any system, if the unit circle is not in the region of convergence, then that system is said to be unstable. At this stage, I hope you can appreciate what I mean by the Z surface and also the idea of the region of convergence. I'd like to point out that when the surface of the magnitude of h of z is being illustrated, the region of non-convergence is often filled in as shown. I find that this view is generally easier to interpret, and in my view is a far more useful illustration, even though it's not correct. In the next video I'll explain how to determine this alternative view of the h of z surface and some of the issues associated with it.